Hi everyone. In this video, as promised, I wanted to go over finishing our Module 2 problems and just doing some of the ones that we already seen in class. And I'm just gonna work through them and give you guys intuition that we should have. So we're gonna go ahead and start off at a limit loss problem. We did this as a class together, but it'll be nice to revisit it. So let's say I was to tell you to find the limit as x approaches 2 of 3 f of x plus 4g of x over h of x. Now you can go ahead and plug in with the givens that are given. So we were given that the limit as x goes to 2 of f of x would equal 5. The limit as x goes to 2 of g of x was -1. The limit as x goes to 2 of h of x would equal 2. Now the reason where limit laws come in is that it's almost a distributive property here, is that first we're going to apply a limit to the numerator and then we're going to second apply it to the denominator. Let's try breaking that down. So the limit as x goes to 2 of the numerator over the limit as x goes to 2 of our denominator, right? So then we can distribute even further with this, as this limit will apply to this term and applies to that term, and of course this one applies to this one. So to save room, just so that we can fit this all, I'll just make this smaller here, and then we'll distribute. So the limit as x goes to 2 of 3 f of x plus the limit as x goes to 2, wait, we need a 4 in the front, 4 limit, wait, I'm going to come back to this. So we're going to continue writing it as is. Limit of 4g of x all over, just make sure this doesn't cut off. I'll put this here and then bring this up. The limit as x goes to 2 of h of x. And now we can take this even further is by the constant rule. And if you don't recall the constant rule, it was basically that some c, if I was seeing the limit as x goes to a of some c of f of x, c being my constant, I can pull it out. The c comes down in the front and my f of x goes here. So let's try doing that. I'm going to pull out the 4, bring the limit up, and then out comes that, and there goes that. Okay. And now we can simplify, and I'll start scrolling down. I want to keep the givens, so let's bring those down. There. And now we can solve. 3, limit of f of x is 5. It's just a plug and chug at this point. 4, -1 over each of x is 2. So 2. And if we simplify, that's 15 minus 4 over 2, meaning we should get 11 halves, right? So that's one limit law. Here's our second problem on limit laws. And once again, it's a simple plug and chug. And so we can start by expanding with limit laws. So I'm gonna go ahead and basically distribute this over. So we have the limit as x goes to 4 of 2 f of x minus the limit as x goes to 4 of 5g of x. Just make this look more like a 5. And then we can just move this down a bit. Here. Times. So all of this times the limit as x goes to 4 of h of x. Let's just make this smaller so that we have a longer. Okay, that is. And now we can bring our constants out to the front. So when 5 comes out, the limit as x goes to 4 of g of x, and then all of this once again multiplied by the limit as x goes to 4 of h of x, and now we can just plug and check. So 2 times the limit as x goes to 4 of f of x is 3 minus 5 times negative 2, all of this times 6. 6, this seems to be a 6 minus a negative 10 times 6. Right, I can make more room for it. Let's bring this down there. And then 6 plus 10, this becomes a plus, right? This is 16 times 6, which is 96. Right? And that's how we do that limit. The next thing on our packet has to do with composite limits. And so that is something I'll talk about in our next lecture, just because it's an extensive topic and I would rather cover it where you guys can ask me questions at the same time. And so moving on, we come down to this idea that when limits don't exist, right? Or we could like actually not exist, but rather when we get like into indeterminate forms, right? For example, like we have a limit such as the limit of x goes to 1 of x squared minus 1 over x minus 1. The first thing we always want to try is direct substitution. And the only time that direct substitution works is when f of a, we'll say f of x, so some function is continuous at x equals a, where the limit, this is our limit, right? So as long as this a is continuous in our function, right? So if I was to plug in f of a, I should get a f of a at this point and to the right and left of it, meaning we should be continuous. We'll talk about definition of continuity, but otherwise, that's all we're saying is it should be continuous. Not defined, right? Because if you think about it, this is like a topic for later, but rather, if I have, let's say, this going on, I can have a hole here, but if I, like if you think about it, in this case, let's say this is 4, right? And this, all this is taking at 2. F of 2 will equal 3, but the limit as x goes to 2 of f of x will be 4. So this is not a continuous case because we have a hole here. And just plugging in a value won't tell you whether something's continuous or not. But keep this in the back of your head. This is a later topic. I just like introducing definitions early so that when they do come to you, they do make sense. Okay. Now let's go ahead and try doing direct substitution on this. So we're going to, I'll bring this down. 1 squared minus 1, 1 minus 1 equals 0 over 0. This is called the indeterminate form. Indeterminate form. In other words, we call this do more work. And this is where algebraic manipulation comes along. So the first method I want to show you guys is factoring. So method 1 is factoring. And the idea of factoring is to get rid of your whole. Well, like in the idea of when you have do more work, is to somehow we can say like get rid of the discontinuity. Get rid of discontinuity. And this doesn't work in all cases, but this is one of the cases. And if you think about it, we don't want to get rid of every discontinuity. When we only want to get rid of discontinuity when there's indeterminate form, which is normally your wholes. And we'll talk about that in a bit. Or at least in next lecture, we'll get to it. So let's go into try factoring. So notation's important here. We're going to look at the same exact limit, x minus 1, and then we're going to factor it. So let's try factoring. We have x plus 1, x minus 1 over x minus 1. We found our whole, right? And we can cross the whole out. So when we cross it out, we now we have to continue our notation properly. And now we can try direct substituting. So 1 plus 1 equals 2. All right? So from here, this limit here, actually, let's say this one can be evaluated with direct substitution. All right? I explained in class why this notation is important. I might make a separate video about this because I don't want to like jumble this one up with that. So for now, try to remember the explanation from class. If not, I'll have a different video. Okay, now let's try this again with a different problem. So we'll do another example. Let's do on the next page. Limit as h goes to 0 of 3 plus h squared minus 9 over h. Realize that we want to, the discontinuity might be at h of 0. So let's try plugging in first. And so we're going to try direct substitution. 3 plus 0 squared minus 9 over 0 gives me indeterminate form. And now I can try factoring. Or at least trying to cancel something. And here's something to think about. I earlier said that this might be my discontinuity, right? Because we're getting determinate form when we have h equal to 0. Meaning, I want to get rid of some factor, right? That's h minus 0 in a sense. That's a factor I want to get rid of, right? Rid. And if you think about it, this is like, we're trying to cancel this out with something on the top, right? So to get to that form, what we can do, I'll get rid of the extra notation, is let's try expanding first. limit as h goes to 0. We'll try foiling the top, right? Or you can memorize an identity. But think of this as this. You can foil the top. I'll bring this down for us. So we're going to have 9 plus 6h plus h squared minus 9 over h, right? Let's keep going though, because we still haven't found a way to cancel out an h. The limit as h goes to 0, I'll put an equal sign to like continue from here. And the 9's go away and we're left with 6h plus h squared over h, and voila. We can just factor out an h in the numerator. H plus 6 plus h. 6 plus h over h. These cancel because you can look at them as factors of 6h minus 0. Like as I was showing you guys earlier, imagine these as factors, right? And we're canceling them out to be left with the limit as h goes to 0, 6 plus h, do direct substitution, and we get 6. So once again, we did direct substitution here. Right? That's this one quickly. And next, we're going to look at a different method. This time, we're going to look at rationalizing. So method 2 is rationalizing. This one we had a long time figure out in class, but there's a pattern to it. So the limit as x goes to 1 of x minus 4, 3 minus x plus 5 square root. And the idea with this is we multiply this by something that's equivalent to 1 to factor out, to change the denominator in a sense, right? So we multiply by this because in a sense, this is just equal to 1. So all we're doing is we're basically moving this denominator to the top with an equivalence, you can say. In these videos, I really want to just try on nailing the concepts, so the details will always be explained in class, but I'll try including them somewhere. So as we go along, I meant, okay. So now we can try the limit as x goes to 1. The thing we messed up in class, and I want to make sure we don't do right now, is these don't get factored. I mean, we don't like multiply them together. We just keep it as is. I think this is where the problem came in class. As x goes to 4. Let's fix that typo and let's see if it helps us. And then now we can multiply the denominator. There's a identity you can memorize. So I'm going to say that a equals 3 and b is going to equal x plus 5, right? And so now if we rewrite everything, we're actually multiplying a minus b times a plus b, correct? Do you guys see that? Like, this is my a of 3, right? That's 3 minus b, that's b, all right? B, and then we do the same thing. 3, so a plus b, a minus b. And the way this identity works, and now you can just FOIL this. So we're gonna have first inside outside last. These cancel out, and we're left with this. And that's a super easy way to do it now because let's just plug and chug. A squared is 9 plus b squared. So think about doing this. 2 square roots cancel, so we're just left with x plus 5. Oh, and I messed it up. This should be a minus. If you caught that, great. And we get that minus because when we do the two last terms, this is minus b times a positive b. So we have a minus b squared. And so now a plus, 9, this is a 9, plus, actually minus the b term, which is just x plus 5. Right? And then we can continue simplifying. I'm going to copy the numerator. Some of you may have already seen what's happening or realized it. We're going to get, so if I distribute the negative sign, we get 9 minus x minus 5, which simplifies to, we can rearrange this to 4 minus x. Let's copy this over. This is 4 minus x. Right? Now, these two are very similar, and we just can't cancel them out. This one and this. They're very similar, but we just can't cancel it out because they're not the same factor. And if you realize, I can get to, think about it. If I multiply x minus 4, actually 4 minus x, by a negative, it gives me something I can rearrange into x minus 4. So if I multiply both my numerator and denominator by a negative, I should theoretically, not theoretically, but I should get the right answer. So let's multiply both by -1. And here's what I'm going to do. The goal is to preserve the factor. I want to preserve this. So I'm just going to put a negative out front. Right? We preserve the factor. And then we multiply on the bottom. So we actually will do a whole computation in our numerator, which we know was x minus 4. And now we can cancel out the terms to be left with the limit as x goes to 1 of just minus 3 plus x plus 5. And we can do a direct substitution. Now we can directly substitute. Let's shorthand this, which will give us the limit as x goes to 1 of minus 3 minus x plus 5. Why do I keep holding it? There. And then we can plug it in. So minus 3 minus, by the way, why am I keep running 1? This is a limit to 4. 4, 4, 4. Wherever. Okay, everywhere I have a 1, it should be a 4. So 4, 4, 4. And then, so we plug in a 4 plus 5 minus 3 minus square root of 9 minus 3 minus 3 negative 6 is our answer, right? Hopefully you're able to follow along. It was sort of long. Like, that's the whole entire problem. But the idea is to not distribute the numerator and just keep simplifying until you can cancel out the factor you want to. And in our case, realize when we would have, I didn't show you guys, but if we directly substitute, we would have got this form, by the way. So when I got that form, I would know I'm trying to get rid of this factor, x minus 4. And that's what you found. And realize we tried preserving it the whole time, right? Until we could cancel it out. That's the goal here of this problem for rationalizing. And then finally, we're going to start our third method, which is honestly our final method that we will cover in terms of AP Calculus. There is other methods, but this is the one that we're going to end off our series with. So let's try to find the limit as x goes to 0 of just x over 1 over x minus 2 plus 1/2. Realize the denominator is actually a complex fraction. And so how do you simplify complex fractions? Let's try doing it on the side. So 1 over x minus 2 plus 1/2. Oh, first of all, you do directly substitute. And so we can try directly substituting. Let's do that. I would get 0 over 1 over negative 2 plus 1/2, and that will give me 0. So yeah, we do get 0. But let's try to simplify our complex fraction. Simplify. We're going to try simplifying 1 over x minus 2 plus 1/2. So first thing, you need common denominators. And so we have two different factors here in our denominator. We have x minus 2 and 2. So let's realize our factors in denominator, called factors in D, is x minus 2 and 2. These are two separate factors, or like denominators that we have. And so my goal is I want both of them to have each other's, right? I want my final fraction to look like and let's think about it. Here in this one, we're missing a 2, and here we're missing x minus 2. And how do we get both of these factors on them? We multiply. We multiply the numerator and denominator by the factor. So I'm going to move this down as this is our final goal. Let's try doing that. We're going to take 1 over x minus 2, multiply the numerator and denominator by 2, and then for our second one, 1 over 2, we multiply by x minus 2, and now we should get, so you can realize the denominators match up now, realize, right? This matches with this matches with that, right? So our denominators are fine. We have 2 x minus 2. And now we can add them both. So I'm going to have 2 plus x minus 2 over my common denominator of 2x minus 2. Realize the 2's cancel, and so I'm just left with x. And now we can try redoing our limit. So back to our limit. Back to limit. I'm going to copy it from the top, and I'm going to show you what we're going to do. Here's our limit. I paste it here. I get rid of my complex fraction, and I bring in my simplified fraction. And if we try simplifying this, right? I like to write out division as a multiplication. So x over 1 times 2x minus 2 over x. And now we have something to cancel, x and x. So now the limit as x goes to 0 of 2x minus 2, I plug it in. Did we do this right? 2, oh yeah, I did. Minus 2, and I get negative 4 as my final answer.